Hello, friends. Today we learn about Principal Component Analysis, PCA. Imagine you're analyzing data with many features, like a customer's age, income, and purchase history. Each feature adds a dimension, making it difficult to visualize and understand the underlying patterns. When data lives in too many dimensions, it becomes complex and computationally expensive to work with, hiding crucial insights. Dimensionality reduction is about simplifying this complex data. It involves transforming your data from a higher dimensional space into a lower dimensional one without losing too much of its essential information. Think of it like taking a 3D object and finding the best 2D shadow that still tells you a lot about its shape. But how do we choose the best lower dimensional representation? TCA's core idea is to find the direction along which the data varies the most. This direction captures the greatest amount of information, or spread, within your dataset. By preserving maximum variance, we minimize the information lost during reduction. Consider these two perpendicular lines. Projecting our data onto the green line, where the data is most spread out, retains a lot of the original variability. However, projecting onto the red line perpendicular to the first squishes the data, losing significant information and making points indistinguishable. PCA seeks the green line, not the red one. These special directions of maximum variance are called principal components. They form a new set of orthogonal axes, ordered by how much variance they capture. The first principal component, PC1, points in the direction of the greatest variance, while PC2 points in the next greatest orthogonal direction, and so on. These components essentially redefine our coordinate system. So, how do we actually find these principal components? The PCA algorithm typically involves a few key steps. First, we center our data. Then, we calculate the covariance matrix to understand relationships between features. Next, we compute the eigenvectors and eigenvalues of this matrix, which are the heart of PCA. Finally, we project our original data onto the chosen principal components. The first step is to center the data, meaning we subtract the mean of each feature so that the data is centered around the origin. This ensures that the principal components are solely dependent on the variance and covariance. Next, we calculate the covariance matrix, which tells us how much each feature varies from its mean and how each pair of features varies together. Now, for the core of PCA, eigen-decomposition. We find the eigenvectors and eigenvalues of the covariance matrix. Eigenvectors are special directions that, when transformed by the matrix, only scale in magnitude, not direction. These eigenvectors are our principal components. Their corresponding eigenvalues tell us the magnitude of variance captured along each eigenvector, indicating their importance. With our principal components identified, we can now project our original data onto these new axes. If we want to reduce our 2D data to 1D, we simply project it onto the first principal component, PC1, discarding PC2. This transformation gives us a new dataset, where each point is represented by its coordinate along PC1, effectively reducing its dimensionality while retaining maximum variance. PCA is incredibly useful in various fields. It helps in data visualization by reducing complex data to 2 or 3 dimensions, making patterns visible. It can reduce noise in data by focusing on the most significant components. PCA is also used for feature extraction, creating new, more informative features, and for data compression, storing information more efficiently. In essence, PCA is a powerful technique for dimensionality reduction. It works by finding new, orthogonal axes, called principal components, that capture the maximum variance in your data. This allows us to simplify complex datasets while preserving their most important information. Thank you for watching. Please like and subscribe for more videos.